Hello everyone, this is Human Hard Drive, and today we're continuing on with our Electronics 101 tutorials. As I alluded to in the last video, today we're going to be talking about the component known as the resistor. And so here is one. This is your standard axle package, not surface mount, sorry, through-hole resistive component. It is a non-polar device. And today we're going to be talking about some of its finer points and some of its applications. So just to go over this, you've got two leads and the main body of it, the package, and I'm sorry you can't see it in this video, my camera's a bit of, it's a piece of crap, but there are these several color bands, and each of these bands means something, and we'll get into that on the video. Alright, so let's talk more about resistance. So, let's talk about the symbol, because we also want to talk about schematics. This is the general symbol you will find on schematics, and then it's got the resistance in ohms down here. And let's just talk about, let's go back over Ohm's law. Remember this? Went over this last time. So resistance, because we care all about resistance, is V over I. And again, this is in units of ohms, which is the symbol omega. Okay, so we're going to talk about, I'd mentioned last time P versus S. We're going to talk about what that means. We're going to talk about the uses for resistors. And we're going to talk about one more thing, because it is technically a resistor. This thing, and I know that's a poor drawing of what it should be, but we'll talk about that towards the end. Although I'd like to mention one more quick thing. When we're talking about resistance, we don't just care about the component that is the resistor. And this is extremely important. So it's so important, I'm going to write it in red. All components have resistance. This is very important. This is oh so very important that people forget about it so often. All components have resistance. The wire you use has resistance. The LED you use has resistance. The light bulbs in your house have resistance. Everything needs to be taken into account. And while we're only going to be talking about resistors, this will be a big thing if you go into digital electronics, where you talk about things like impedance and tri-state buffers. These things are very important. So, bearing that in mind, we're going to remember that. We're going to come back to that later when we talk about things like capacitors and other such things. But for now, let's just move on. So, P versus S. What does that mean? Well, that's parallel versus series. So here you have parallel versus series in terms of resistances, and there are a couple things to remember when it comes to parallel and series. Parallel is a resistance divider, whereas series is a resistance stacker. Now, if we go back to Ohm's law, which is going to be very important, hail Ohm's law. We keep highlighting that until you remember. We're going to talk about current. Now, when you talk about resistors in parallel, current changes. Whereas in series, current is constant. And because voltage and current are interrelated, voltage is constant, whereas voltage changes. We're going to hit on that why. We're going to talk about why in just a moment. So, parallel. What is a parallel resistive circuit? I know I misspelled that. I'm an engineer. I don't need to know how to spell. Yeah, I'm just kidding. Everyone should know how to spell. Very important. So, here's your 5 volts. And there's a node. There's resistance. Here's a resistor. Tie these two together. And this is the symbol for ground. I'm not sure if I mentioned that. Very important to know. That's ground. I pick 5 volts because I do a lot of digital circuits, and 5 volts is sort of that's the voltage you always want to come back to, generally. This dot here is a node. It means I'm connecting 2 wires. And I'll put one here as well. Okay. So, parallel. R1, R2. You're going to care about something called total resistance, which is the sum, not always the sum, of these two resistances and how they play upon the current being drawn from your voltage supply. Now, it is a as I mentioned, it is a resistance divider. Now, this has great applications if you're trying to find a very specific resistive value. Well, resistors come in a variety of flavors. You can find resistances in almost any value. 100, 220, 47s. They come in so many varieties. But if you come to this point and you're doing some really advanced stuff, I've done stuff with transistors where I've needed 28 point some odd ohms of resistance, and I needed to get, and they don't make them in fractions of ohms, so, or at least I couldn't find them. So coming back to parallel and series is very useful. So let's talk about total resistance. Now, it is a resistance divider, and there's your division. 1 over RT is 1 over R1 plus 1 over R2. Now that divides, so let's say R1 equals R2 equals 100 ohms. I like to pick large whole numbers for my values. So 1 over 100 plus 1 over 100 equals exactly 2 over 100, which is 1 over 50. So 1 over RT, it's a T, equals 1 over 50, which equals 50 ohms. Would you look at that? You started with 200 ohm resistors, and you've come to 50 ohms. So you've just divided the resistance. Isn't that incredible? So this is a formula to remember. Now let's talk about series. Okay, so you've got your 5 volts. And here's resistor 1, here's resistor 2, and here's your ground. I'll even put a dot in here so you know what the two are. 1, here's R2. So if you want to calculate your total resistance, RT equals R1 plus R2. Again, it's a voltage stacker, so it's not dividing. All you're doing is taking all the resistances in series and adding them up. Okay, so what does that mean? Well, it means you can take, say, R1. Oh, let's get rid of that. Say R1 is 50. R2 is also 50 ohms. So the RT is 100 ohms. So the total resistance. So when I'm saying total resistance, what I mean is this circuit can ultimately be reduced down to one resistor. So you've got your 5 volts, you have your resistor, and then you've got ground. And this is our total. That's it. There, it's not going to where I want it to. So you can take this down to one resistor. Same thing goes for this. I can take this entire thing and bring it down to this. So I can replace this entire thing with a 100 ohm resistor, and I can replace this thing with a 50 ohm resistor. Now, I talked about current change and voltage change, and you're going to ask why. Well, let's talk about why. So when you talk about parallel, and instead of writing this all out again, I'm going to be smart. I'm going to copy. I can do this. Copy. And paste. And I'll redraw some of that stuff. No harm. Okay. So here's your parallel circuit. Now, I should make a note that, this is a good thing to remember, current is lazy. Now, I'm sure you've all heard that electricity takes the path of least resistance. That is true, but there is an addendum. Proportionally, electricity takes the path of least resistance, meaning that depending on what the resistance is, most of it's going to go some way, and then the rest is going to go the other way. So, if I've got 5 volts here, and I'm going to use red to represent current, so, oh, whoops. Let's undo that. There we go. So, here comes my current. And at this node, it's going to split into I1 and I2. Now, this is where circuit analysis comes in, which is a useful skill, but we're not going to talk about it right now. If you want to talk about it later, bring it up in the comments. So, remember, current is lazy. So, if R1 is bigger than R2, most of the current is going to go to R2. If R2 is bigger than R1, most of the current's going to go towards R1. And that's what I mean by it's dividing the voltage. Or not dividing the voltage, dividing the current. So if we go back to Ohm's law, where is it? There it is. And I'm going to try to do this, well, we will have to go into a little bit of circuit analysis. So let's say we use the same thing we used here. I'll just copy and paste it again. See if I can, okay. Copy, paste. So let's say R1 equals R2 equals 100. This is a bad example, but we'll go with it. We know that the R total worked out to be 50 ohms. Okay, so if you calculate V equals IR for that, we know the voltage is 5 volts. I'll just I'll rewrite current is V over R. So that's, what is that? That's 5 over 50, which is 0.1 amp. Okay, so we know that the total current through the system, through the equivalent resistance, this is called the equivalent resistance method, which again goes into circuit analysis, which I don't want to talk about because it's very mathy. So it's talking about the current flowing through this resistive system. So there's 0.1 amp flowing through the system. Now if we look at I equals V over R1 and I equals V over R2, you know that the current is 0.1. You know the current's 0.1 here as well. Voltage is 5 volts and the resistance is 100. 5 over 100. Why did I do that? That's wrong. Sorry. Get rid of that. Okay. And you can solve for this. So, if these two resistive values were different, you'd see a difference in current. But they're not, so you're not going to see the change. But the point is that when you total these things up, let's call this, there we go, I1, I2. I1 plus I2 must equal I. So these two things summed together have to be this. So this is obviously 0.05 amps, and this would be 0.05 amps, which summed together will give you that. So it's dividing the current. It's changing the current throughout the system. It doesn't stay constant, because the current at this point will be different than the current at this point. Okay. So if the copy and paste worked so well last time, let's try it again. So I take... Oh, not doing... And the copy and paste is refusing to work. Lovely. Okay, we'll do without. So, series... Oh, I should go back and talk about this. So, even though the current is different, okay, the voltage is still staying the same, because there's still 5 volts going this way, and 5 volts going this way. Now, while current and voltage are tied together, the 5 volts is still flowing in equal portions. That's going to change here. So you've got your 5 volts. And here's resistance 1, here's resistor 2, and R1, R2. Okay, this time I'm going to give them different values. Okay. Now, last time I talked about voltage choking, which is it's sort of this overflow of current and voltage that wants to move somewhere else. So, if we look at this here at different points, look at this, if we look at this, these two values are different. So the choke is different in both these spots. Now, if we look at R1, if we go back to the total, where is it? Here it is, total resistance. If we add these two things together, we get 110 ohms. Okay. So this entire thing is the same as 110 ohm resistor. So if we go back to I equals, I'm going to draw current. Now, I said current stays the same throughout the circuit. And it's true, and I will prove it to you. I equals V over R equals 5 volts over 110. That's 100. There we go. That's 110. Equals, well, you can do that out. Okay, it's 22 amps. So 1 over 22 amps. Alright, so because it's flowing in the same direction, okay, there's no splitting, current can't be lazy. Current has to go the only way it can to ground. So it's not going to try and split, it's not going to try and fork. This is going to effectively act as one resistor and give you 1 over 22 amps flowing throughout each one. That being said, the voltage change is different, because there is going to be, while there is 1 over 22 amps flowing through the thing, this is where it gets a little weird. There's a choke, there's like this excess of electrons waiting to flow through the resistor, and there's this excess of electrons being held up waiting to flow through the resistor. It's that, if we go back to the hose analogy, it's that water that's waiting to be pushed out of the opening. It's still sitting there, and that's the voltage. So here's your V1, and here's your V2. Now V1 is directly connected to the 5 volts, so this is ground. 5 volts, why did I say ground? This one is in between. So whereas this is a current divider, this is a voltage divider. See? And this is an extremely useful thing to know, because you can create, well, you can split voltages. So if something needs 2.5 volts and you've got 5 volts, well, if I've got 200 ohm resistors, I can make 2.5 volts easy. So it's, the division is a ratio between the choke here and the amount flowing, or the amount this chokes and the amount that's flowing through. So that is R2 over R1 plus R2. So it's the total resistance, the total amount of stuff flowing through underneath the choke that this resistor's adding, that this resistor is creating. So it's the stuff that's spilling out here. So it's like a barrel you're trying to fill, and some of it's flowing over because it can't empty out fast enough. So this is that ratio. So this will give you a number between 0 and 1. So we need to change that. We need to multiply that by V in, and that gives you V out. And this is an extremely important equation to remember. Now, I should point out that this doesn't always hold true in a very specific case. If you're drawing too much current here, this V out will change because it's going to start drawing more and more current through here and making this value less and less important. So just keep that in mind. We will talk about that, and there is a way to deal with that, but for now, don't worry about it. If you're doing something where you need a reference voltage for like an Arduino or an op-amp, this is the perfect thing. But if you don't, again, those are high impedance things, which we're not going to talk about. Well, I'll have another series when this is done, but we're not going to worry about that right now. Voltage divider, very useful to know. Okay, so I had mentioned back at the beginning, where was it? Here it is. I had mentioned this thing. Okay, what is it? Well, for those of you that might already know, this, I'm going to draw it better, there we go, is called a potentiometer. Now, the potentiometer is like two resistors put into one. So it's a 3-pin device, which I wish I could draw. You've probably seen what these look like. I wish I had one to show you, but it's generally like a box, and there's a pin here, and there's a pin here, and there's a pin out here, and there's a dial that you can spin to change the ratio between the two. So between these two pins is your R total. Between these two pins, here's R2, here's R1. And R1 plus R2 equals RT. Now wait, doesn't that look like this? Yes, it is a series resistor, which means this thing can effectively act as a voltage divider. So if I take this, let's label the parts. This thing right here, this arrow is the wiper. So I'll make a note in a different color so you don't get confused. This is called the wiper. It's the thing that slides across. Oftentimes it's a carbon track to change the voltage across, or to change the resistance across the device. So let's say you've got 5 volts here, and here's your potentiometer, and this is connected to ground, and then there's your wiper. So here's R1, here's R2, and here's the output. And so this is your V out, and it's the ratio, depending on how much that dial is turned, between these two things. So this is useful. Again, you can just use one side of the device. You can just flow from here to here to vary the current, or you can go from here to here, or you can use the whole device to get a voltage divider to set up a reference voltage. Okay, so let's just sum up, because I think we went over a lot today, and it's always a good idea to sum up at the end. Resistance. What is it? It's the ratio of voltage to current in a system, and it's measured in ohms. We've got the symbol here for it, which you will see in schematics. Good thing to know. All components have resistance, which we will talk about more in later videos. Parallel versus series. These are good things to remember because they're going to affect how a system changes. Parallel circuits are resistance dividers. The current changes, but the voltage remains constant, as we can see here, as I demonstrated. Well, not very well, but if you change these resistances, you can prove it out to yourself. And total resistance. Replacing two resistors with one, it's dividing the voltage. Good equation to remember. Series. It's a resistance stacker. The current remains constant as opposed to the parallel, and the voltage changes as opposed to parallel. So, again, another good equation to remember. Replacing two resistors with one. What's that called? Equivalent resistance. Another good equation to remember. Voltage division throughout a series circuit. And finally, the potentiometer. It's two resistors packed into one device, and it's got a dial. Note, these are things you've probably seen on, like, these are your speaker knobs, or if you had an old style thermostat, which actually isn't a potentiometer per se, but your volume knob on your speaker, or your other various components. And yeah, that's it. So we talked about resistance today. Next week, it is the viewer submission, but I haven't received any requests. So it's actually next week. It's the week after next. So again, if you have any questions, I'd mentioned circuit analysis, which we could go over in the next video. If you have any questions, be them far advanced from what we're doing, please ask them. But if no one submits any questions, by the way, questions can be submitted in the comments below. But if you guys don't have any questions, if there are no comments posted, and based upon your track record thus far, it's not looking good, we're going to talk about a very important component, which actually deals a lot with these. Capacitors. What are they? What do they do? Why do I care? All good questions. So, this has been Human Hard Drive. Thanks for watching.